Hello and welcome guys to Sonic the Hedgehog, and in this video we're going to talk about real power, apparent power, and power factor. So what is power, you ask? Well, power is the demanded power, basically is the demanded power that your device draws. For example, when you plug a microwave into the outlet and turn it on, the power is what it uses. Well, basically how much electricity it uses. You can see that we'll use the beer analogy. So this is the whole pint of beer. Now, then, by the actual power factor of the device, you divide it into real power and apparent power. The real power is the beer that you're going to use up, and the apparent power is the wasted power, or reactive power is the wasted power that the device wastes. And that's normally with big inductive or capacitive loads. When it is a capacitive load, when it is an inductive load, now I forgot it. Basically, when it's, for example, a big bad inductive load, the current leads the voltage, and if it is a capacitive load, the current lags the voltage. Let me show you. So here, if you, for example, take an inductor and put it here, this is a pretty terrific load to work with. Basically, inductors are pretty bad loads. So take for example that, well, basically no. To actually show you, we'll have to talk about the power factor, and the power factor is basically how much of the power you're using, and the power factor is calculated by wasted power divided by useful power. And basically, the power factor tells what percentage of the actual demanded power is useful power. So here, power factor is calculated by true power divided by apparent power. So for example, the power factor is 119.365 watts divided by 169.256 volt amps. Now, actually, for normally you're familiar with watts or kilowatts or milliwatts, but you don't use watts for apparent power. For apparent power, you use volt amps, and they are basically counted the same way as watts. So basically, P equals V over I think. So that's current times voltage. Anyways, here's your power factor, and the power factor is basically counted like this. So 0.7705 was back in the day a good power factor, but today is considered terrible. Anyways, so that's what power factor is, and here you can see really complex calculations. You can see that power factor isn't only called PF, power factor, or PF for short, but it's also called cosinus phi or cosinus phi, and there's even something called sinus phi. It isn't easy. Anyways, you can see the phase angle here and all that. I'm not going to explain that to you because you don't need it. Here's basically your standard calculations that you see right here. So back to the thing. So let's say that this inductor has a power factor of 0.45, for example. And if we want to make the power factor better, we would take a capacitor and connect it, and we would take a capacitor and connect it across the inductor to make the power better. And by this, your power factor is suddenly much better at, for example, 0.915. Now, for difference, if we take a big capacitive load and want to make its power factor better, we do the opposite, and we take a inductor and we get rid of this. We take an inductor and connect that across the capacitor, and let's say it's got a power factor of 0.01 and it makes it to around 0.85, which is still in this day and age considered bad power factor. but it's still kinda good. You know it. Anyways, so yeah, that's that. But power factor circuits can be more complicated. So if we go and search power factor correction, and you head to Google Pictures, you see that this is what's called a power factor correction. Now, these are active power factor correcting units, meaning that you have active and passive. The active use a specialized boost converter circuit as well as a rectifier to make the power factor better, and the passive ones just use a big inductor or a capacitor. Basically, yeah. This is the actual schematic of. Let me basically. This is the actual schematic. Let me put it onto the. This is the actual schematic of one of those boost circuits. Let me zoom in a bit. So I'll explain. So AC goes into the full bridge rectifier. Then from the full bridge rectifier goes through an inductor, which is switched by a PWM controlled MOSFET, raising the voltage to 240. No, let me do it again. So AC goes into the 230 volts AC 50 hertz goes into the full bridge rectifier. From the bridge rectifier, it's turned into 230 volts DC. Then goes through an inductor, which is switched by PWM controlled MOSFET, and it turns it into 400 volts DC. Basically AC 400 volts AC. Then it's rectified by a diode, smoothed out by a capacitor, and straight to the load. So that's a boost converter power factor correction circuit. There's also much more complex ones. You can take something like this, for example. Yep, this is something like this. This is what I call biactive power factor correction. Yes, this is active power factor correction. So yes, this is passive power. Is this active or no? That's passive power factor correction, because you have only capacitors and inductors and just contactors, and the contactors are only switches as well as breakers. Those are basically protection switches. So yeah, am I recording? Yes, I am. So that's power factor correction. And yep, going back to the stupid energy saver, something like this. I'll draw you out the schematic again. So we shall do blank circuit, and we'll start by getting wire. And so I'm gonna going to explain the circuit. So live goes in. Then let me take a switch. Then goes through a switch. Then it goes through a fuse. And then goes into the magic black box that you will find inside one of these. And that's a big ass capacitor. And it's basically got a discharge resistor across it as well. This will just make it safer, you know. So add some wires and connect that across there. There we go. Then the current coming from the capacitor, and this is now only the inductor circuit. And that goes, give me active components. Then it goes into a diode to rectify the current. Then from the diode, it goes into a resistor. And then from the resistor, it goes into an LED. I don't know why it makes that stupid circle on the LED anyways, doesn't matter. And then you got the input. And that's it. And how it's working? Simple. When you turn the switch on, it goes through the fuse, then goes into the capacitor, which does the power factor correction. These ones are, by the way, hoping that you basically have a device which basically on this one they are hoping that you have a inductive load. Next of all, you got a discharge resistor to discharge it so it doesn't give you a zing when you unplug it. Then this is just the circuit for powering the LED, a rectification diode resistor, and the LED. Now, what I would actually do to make this better is I would take an inductor, and it would be as simple as that. Just take an inductor, and just put it across the capacitor, and that's it. Why? Well, that's because when you don't have any inductive load with it and a capacitive load, it will make the power factor worse because you're adding another capacitive load across it, remember. But by putting an inductor across this, you're not only making the power factor of this capacitor better, but you're also making the power factor of the actual capacitive load that you are connecting this to better. Does that make any sense? I hope so. Anyways, basically, yes. Yes. So that's that. So that's basically the power factor correction explained. So I hope you like this one, and I'll see you guys in the next one.